Hello, myself Dr. Sudha from Government Science College, Autonomous, Bangalore. In this session, let us study about standard applications of calculus of variation. The learning objectives are the minimal surface of revolution as well as hanging cable problem. The prerequisites are the basic integration is required, concept of principle of minimum energy, Euler's equation, and particular forms of Euler's equation. Let us begin with history. In 1686, Isaac Newton proposed and gave solution to the surface of revolution of minimum drag when the body is moved through a fluid. Minimal surface of revolution. Any freely hanging cable or a string assumes this shape, and this is called chainade. In 17th century, the Dutch mathematician Christiana Huygens showed that the chain curve cannot be given by an algebraic equation. Then what is that curve and what is its equation? It is catenary. Catenary is a curve that describes the shape of a flexible hanging chain or cable. The name derives from the Latin word catenaria, which means chain. Huygens coined the term catenary. In addition to Huygens, the Swiss mathematician Jacob Bernoulli and the German mathematician Gottfried Leibniz contributed to the complete description of the equation of catenary. The curve in xy plane is given by y is equal to a by 2 into e to the power of x by a plus e to the power of minus x by a, or it can also be expressed in hyperbolic functions as y is equal to a cos hyperbolic x by a. The surface of revolution generated when an upward opening catenary is revolved around the horizontal axis is a catenoid. So this is the catenoid and this is the curve catenary. The catenoid was discovered in 1744 by the Swiss mathematician Leonardo Euler, and it is the only minimal surface that can be obtained as a surface of evolution. Do the creators of the skateboard ramps know that the fastest ramp has the shape of a cycloid? The answer is yes, according to one of the article, but apparently no cycloidal ramp was ever created. Let us begin with the minimal surface of revolution. The statements is stated as the curve which when rotated about a line generates a surface of minimum area is catenary. Let us prove this. Let us consider P and Q. P is x1, y1 and Q is x2, y2. Be any 2 points on the plane curve. Let us rotate the curve about the x-axis. So this is point P and this is point Q, which lies on this curve, and this curve when rotated about this axis, that is the x-axis, a catenoid is generated. And let us take a small strip with the bandwidth ds, that is the arc element ds, And let us cut open this. We get a circular strip. Cut this circular strip, and when it is spread over, we get a rectangular shape with width ds and the length is 2 pi y. Why this is length 2 pi y? Because the length from this point on the x-axis to this point on the curve, let us take that to be arbitrary y. And this will become the radius of this circular strip. And since the length is the circumference of this circular strip, we know that circumference is given by the formula 2 pi r, where r is the radius and here the radius is y. Therefore, the circumference of this circular strip is 2 pi y. Therefore, the length of this rectangular strip is 2 pi y and width is ds. Therefore, we get the elementary area to be 2 pi y into ds, that is length into breadth. So, area of that rectangular strip is denoted by A and that will be equal to 2 pi y ds. Therefore, the surface area of the surface of revolution, that is the entire catenary, the surface area of this entire catenary is given by S is equal to integral P to Q A, where A is the elementary arc length. Let us substitute for A, we get 2 pi y ds. And the limits now become x1 to x2, where x1 and x2 are the x coordinates of the point P and Q respectively. But we know that the elementary arc length element ds is given by square root of 1 plus dy by dx whole square into dx. But what is dy by dx? It is y dash. So we can put ds as root of 1 plus y dash square dx. Now let us substitute this value of ds in the expression for the surface area. Therefore, we get S is equal to integral x1 to x2 2 pi y root of 1 plus y dash square dx. Now for S to be minimum, it must satisfy the Euler's equation dou f by dou y minus d by dx of dou f by dou y dash equal to 0. So here what is f? F is the integrand here. So we can take f to be equal to y into root of 1 plus y dash square. Here we can delete this 2 pi, which is a constant. Let us take only the function which contains the variables x, y and y dash. So here f is equal to y into root of 1 plus y dash square, and here we can see that there is no x term, therefore it is independent of x. Therefore, the corresponding Euler's equation when f is independent of x is given by f minus y dash into dou f by dou y dash equal to c, where c is a constant. Now let us substitute for f, that is y into root of 1 plus y dash square minus y dash into dou f by dou y dash. Let us differentiate f partially with respect to y dash. So we get, keeping y as it is, y by 2 into root of 1 plus y dash square into 2y dash, that is derivative of this inner function 1 plus y dash square gives us 2y dash, and that is equal to c. So let us simplify this. So on simplification, that is cancelling out 2 and 2 here and taking the LCM, we get y into 1 plus y dash square minus y into y dash square. So on simplifying further, we get y divided by root of 1 plus y dash square on cancelling y into y dash square with minus y into y dash square. So this is the expression now. So let us square both sides because we need to solve for y dash from this expression. On squaring both sides, we get y square by 1 plus y dash square is equal to c square. So on cross multiplying and shifting the terms, we get y square minus c square is equal to c square into y dash square. And solving for y dash here, we get y dash is equal to root of y square minus c square divided by c. But what is y dash? That is dy by dx. Therefore, dy by dx is equal to root of y square minus c square divided by c. And now let us separate the variables. So on separating the variables, we get dy by root of y square minus c square, and that will be equal to dx by c. This is obtained by separating the variables. Now let us integrate to obtain the value of y. So on integration, we get cos hyperbolic inverse y by c is equal to x by c plus k. The left hand side gives us cos hyperbolic inverse of y by c. It is one of the standard integral, and integral dx by c will give us x by c plus k, the constant of integration. And let us simplify this right hand side by taking the LCM. So we get x plus kc by c, and that is equal to cos hyperbolic inverse y by c. Here we need to solve for y. So we get y by c is equal to cos hyperbolic of x plus kc by c. Let us put kc is equal to another constant, that is a. So kc is equal to a. We get y by c is equal to cos hyperbolic x plus a by c. So let us solve for y here, that is cross multiplying c to the right hand side. We get y is equal to c into cos hyperbolic x plus a by c. And we know that this is the expression for the curve which makes the surface area of revolution minimum. But this represents the curve catenary. Okay, y is equal to c into cos hyperbolic x plus a by c is nothing but a catenary. Therefore, the minimal surface of revolution is obtained when a catenary is rotated about the fixed axis. Here we took it as x-axis. Hope everybody followed this minimal surface of revolution. Next, let us move on to hanging cable problem. What is this hanging cable problem? By employing the principle of minimum energy, show that the shape of hanging cable, which is freely suspended cable, is a catenary. Once again, we need to prove that the hanging cable shape is nothing but a catenary. Or it can also be stated as, if a cable hangs freely under gravity from the fixed points, then show that the shape of the curve is a catenary. So let us prove this now. So for that, let us take 2 points, A, x1, y1 and B, x2, y2, be the fixed points from which the cable is suspended. So if we draw the curve in xy plane, we get the shape like this. This is the shape of the freely hanging cable. A is fixed, that is x1, y1, and B is fixed, that is x2, y2, and ds represents the arc element, and the height of this cable from the x-axis is taken to be y. If ds is the arc element and rho is the density, that is mass per unit volume, then the mass of the element is given by rho into ds. We know that mass of the element is given by density into the length of the element, that is length of the element, that is arc length is ds and the density is rho. Therefore, mass is given by rho into ds. Now let us apply the potential energy with the x-axis as the reference. So potential energy is given by mass into gravity into height. Therefore, mass is rho into ds, gravity is taken to be g, and height, we have seen that the cable is at the height of y units from the x-axis. So therefore, we know that the potential energy is m into g into h. M is mass, g is gravity, and h is height. Therefore, mass is rho ds, g is taken as g, and y is height. Therefore, here y, where g is the acceleration due to gravity. So let us find the total potential energy. Let us denote that by capital P, and that is given by integral x1 to x2. That is, we are integrating from the fixed point A to fixed point B. So the x coordinate of A is x1, x coordinate of B is x2, into the potential energy element here, that is rho ds into g into y. Here let us substitute for ds, because we know that ds is nothing but square root of 1 plus y dash square into dx. So on substitution, we get v is equal to integral x1 to x2 rho into root of 1 plus y dash square dx into g into y. So let us remove this rho and g, which are the mass per unit volume, that is density is a constant, so you can remove it outside, and g, the gravitation due to acceleration due to gravity, that also is a constant, you can remove outside the integration, and we are left with integral x1 to x2 y into root of 1 plus y dash square dx. Now this potential energy to be minimum, that is V to be minimum, it must satisfy the Euler's equation dou f by dou y minus d by dx of dou f by dou y dash equal to 0, where f is taken to be y into root of 1 plus y dash square. Once again, it is independent of x, and we can substitute the values of this f is equal to y into root of 1 plus y dash square in the equation to Euler, which is obtained when f is independent of x, that is f minus y dash into dou f by dou y dash is equal to c, where once again c is a constant. So this is one of the particular forms of Euler's equation. Now let us substitute for f and dou f by dou y dash. F is y into root of 1 plus y dash square minus this y dash into derivative of f with respect to y dash, partially we get y divided by 2 into root of 1 plus y dash square into 2y dash is equal to c, which is similar to the expression which we obtained for minimal surface of revolution. Now let us simplify this. On simplification, that is after cancelling out 2 and taking the LCM, we get y into 1 plus y dash square minus y into y dash square divided by root of 1 plus y dash square is equal to c. So here we can cancel out y into y dash square minus y into y dash square. So we are left with y divided by root of 1 plus y dash square is equal to c. From this expression, we need to solve for y dash. So let us square both sides, and we get y square by 1 plus y dash square is equal to c square. From there, on cross multiplication and shifting c square to the left hand side, we get y square minus c square is equal to c square into y dash square. Here let us solve for y dash. That gives us y dash is equal to root of y square minus c square by c. But what is y dash? It is dy by dx. So dy by dx is equal to root of y square minus c square by c. Now let us separate the variables. We get dy by root of y square minus c square is equal to dx by c. Let us integrate. So on integration, the left hand side is in the standard form. So we get cos hyperbolic inverse of y by c. And on the right hand side, integral dx gives us x by c plus another constant of integration k. So let us solve for y here. So we get, here we are solving this right hand side and we write x plus kc by c. Now let us solve for y. So we can write y by c is equal to cos hyperbolic of x plus a by c, where a is nothing but k into c. Now cross multiply c to the right hand side, we get y is equal to c into cos hyperbolic of x plus a by c, and this is the curve catenary. Therefore, the shape of the hanging cable is a catenary. Hope everybody could follow the hanging cable problem. So these are the two standard applications of calculus of variation. In the next session, let us see one more standard application, that is Brachistochrone problem.